Thank you so much for your kind introduction, and also thank you for inviting me to give this talk here. That is a great opportunity for me to summarize some of my recent works in the last 5 years about the formation evolution of global clusters. So actually, a few weeks ago, I made a last-minute decision to attend a conference this week in Arizona, but I forgot the time difference between New York and here. So now it is 6 a.m. So I'm still in my sleeping mode. So forgive me if my brain may occasionally stop during the talk. So if there's any questions that you want me to clarify, go ahead and interrupt me. That is fine with me. So yeah, today I'd like to talk about a topic that I've been fascinated since the start of my PhD. That was almost 10 years ago. Is the origin of globular clusters. So we are all familiar with this type of object, right? They are kind of round, they're massive, they're isolated from their environment, and I would say many people view these objects as kind of boring. Yeah. So so here is this typical globular cluster. What the M15. So this is one of the brightest globular clusters in the sky. And under some good conditions, you can actually see this with your naked eye. But it will look a lot fuzzier. It's like a fuzzy cloud of star. But with HST, so this is the image that you'll be amazed that this is actually beautiful. And you'll be astonished by the density of the stars over such a tiny volume. So it has so for this particular globular clusters, it has a half mass radius around 3 parsec, but it holds more than 100,000 of stars. So we also know that for globular clusters, the few characteristics is that they are very, very old, and they have very poor metallicities. So for a long time, people speculate that they may be formed from some exotic mechanisms under the special conditions of at high redshift, such as some direct collapse scenario of mini halos at the core of the dwarf galaxies and during reionization. And on the other hand, it seems that globular clusters are floating around the galaxies and do not interact with the other components of the galaxy. Therefore, they are usually treated as the excellent laboratory for stellar dynamics, because the so-called spherical model here, spherical cloud model here is not actually assumption, because globular cluster is overall a spherical shape. But are these globular clusters really that simple? Do we, can we just treat it as as simple as a spherical cow? Not necessarily. So it was until a few decades ago, people start to get more and more observations of these objects and making the whole kind of a paradigm shift for the origin of these globular clusters and their interactions with their galaxies. So there are quite a few observations that I would like to mention, but so I just pick 2 of these. The first is the populations of our Milky Way globular clusters. As you can see, although many of these clusters are metal poor, they are not metal free, and they have a wide distribution from this iron metallicity minus 2.5 all the way up to even solar metallicity. So instead of a very narrow view of extremely metal poor, so this broad range of metallicity actually suggests that they co-evolve with their host galaxies. And secondly, there's at the end of 2010-ish, so there's a suite of observations that try to study the globular cluster systems and their relationship with their host galaxies. That is on the right-hand side of this image. So the x-axis is the total globular cluster system in different galaxies. And on the y-axis, this is the total mass of the galaxy. So you can see there's a tight and linear correlation between the total mass of the globular cluster system and the host galaxy mass. And the y-axis is not the galaxy mass.
Sì, sì, ma tanto è un...
Yes, it's not the galaxy mass, it's the total mass, including the dark matter halos. It's the kind of total mass of the whole system. So this is kind of strange because, you know, we kind of assume, you know, the globular cluster is the stellar component of the galaxy, but why it is connected with the total or the halo mass of the system. So there seems to have some connections between the globular clusters and the halo assembly history across such a wide range of galaxy halo masses. So this is very intriguing and suggesting that if we want to study the population properties of globular clusters, we have to take into account their host galaxies. And this makes the whole origin of the globular cluster very complicated, because we need to understand this, you know, the detailed star formation history at this at parsec scale for the star cluster formation. We also need to understand their environments and their hierarchical nature of their structure formation. So typically, after this type of progress, people start to make progress in terms of modeling the globular clusters in cosmological context. So because of the huge dynamical range, people you know, make some compromise from this end or the other end. For example, during the last 10 years, my collaborator and I have been developing several kind of semi-analytical model that try to paint the galaxy, paint the Milky globular clusters into either a n-body or hydrodynamical cosmological simulations, and try to use some empirical relations to sample this globular cluster and to study the scaling relations of the globular clusters in different types of galaxies. And we are actually making many progress in terms of reproducing the scaling relation that I mentioned above. And so this is one type of simulation, you know, but the advantage of this is really fast because it's a semi-analytical model. But the drawback is there are many assumptions that may affect the results of the semi-analytical model. And these assumptions are kind of hand wavy, and it's very hard to be proved to be right or wrong. On the other hand, there are another type of cosmological simulations, for example, in the fire simulation or the very recent so-called Griffin simulation. So the idea is that they use extremely high resolution. They have this massive resolution of a solar mass in cosmological simulation, which is extremely computation expensive. And they study actually the formation part of the globular clusters at a very high redshift. And for some of these simulations, they can actually resolve how these star clusters are formed at the dense blob of gas at a high redshift. But the issue is, you know, these simulations are fantastic, but the issue is they're so computationally expensive, and they can only afford to run a very tiny fraction amount of the cosmic time, and they cannot study the evolution of the clusters. So so in the last 5 years, I have been designing a alternative way of basically bridging these two scenarios by designing a new way of star cluster formation in cosmological simulations. So I use the adaptive refinement, mesh refinement code called ART, with 3D ready to transfer and many other physical ingredients that associate with the star cluster formation. But what I did that is completely different from other cosmological simulation is that in the simulation, each star particle that represent a individual star clusters. So I have a single particle approach that seed this star cluster particle at the center of the resolved giant molecular clouds in the simulation. And then I allow this gas to accrete onto the star cluster particle so that they can grow their mass. So with the high time resolution, I can resolve the growth history of individual star clusters that are formed in the molecular clouds in the cosmological simulations. And when we also include all sorts of stellar feedback processes from radiative feedback and stellar winds and supernovae, so that the mass growth of this particle will be stopped simultaneously by their own feedback. Therefore, the final mass that are obtained by these star clusters are self-consistent and represent the actual mass of the star cluster that are formed within the molecular cloud in the simulation. And so we have very high resolution. We have spatial resolution about 3 parsecs, so that we, for the giant molecular cloud in simulation, it is sort of resolved because that is what we want. But also, this is, you know, less computationally expensive than the direct resolving scenario, but it's still quite computationally expensive. We can only afford the simulation of kind of a zoom in of simulations of Milky Way sized galaxies. So a few things to note about our results. One thing is the global properties of the Milky Way sized galaxies. So in our simulation, the fiducial model, you can see that it roughly reproduced the star formation history of our Milky Way sized galaxies. Even we, you know, change the our different star formation prescriptions. For example, the different lines that have different star formation efficiency indicate the use of value of the local star formation efficiency per free-fall time. And we can see that as long as this efficiency is in this kind of large range, we can reproduce the, you know, it doesn't change the star formation rate that much, meaning that the global star formation history is largely controlled by the star formation feedback interaction. But does it mean that we can choose the star formation efficiency per free-fall time as we want? This is kind of the argument that many you know, galaxy simulation people have been, you know, trying to convey in the last several years, including the fire simulation, you know, saying that, you know, this epsilon free-fall is a parameter that doesn't matter at all. So we can just choose, for example, 100%. So here it is true that it doesn't change the global properties of the Milky Way sized galaxies. But what about the properties of the globular clusters or star clusters that are formed in my simulations? So what we find is that by changing this star formation efficiency per free-fall time, it changes dramatically the scaling relations or the properties of the populations of the young massive clusters that are formed in the simulation. For example, on the left-hand side, so I show observations and the simulation comparison of the relationship between the star formation rate, surface density of one patch of the galaxy versus the maximum star cluster mass that can be formed within this pieces of galaxies. And from the observations that have been labeled as stars, there seems to be a strong kind of correlation between these two values. So the higher the star formation rates, surface density, the galaxy patches are, you know, this indicate the more intense star formation in this region. The higher the maximum star cluster mass that can be formed. For example, for this very high star formation risk density case, you know, some of these many massive clusters with 10 to the 6 solar masses can be formed. And on the other hand, there's also a strong correlation between this star formation rate surface density versus the star formation, the cluster formation efficiency of this region. So the cluster formation efficiency essentially describe the cluster formation rate divided by the total star formation rate of this regions of galaxies. There's also a positive correlation. So we find that in our simulation, we reproduce this positive correlation. And we also find that the normalization of these relations really depends on the choice of the star formation efficiency per free-fall time. So we argue that we should use this kind of more spatially resolved properties of star forming regions or star clusters to actually constrain the star formation efficiency per free-fall time. So this is not a free parameter that we can, we can choose whatever we want. There's some fundamental difference on small scales of the galaxy that should be constrained by observations. So this is the formation part. We formed a lot of massive star clusters. And what are the dynamical evolution of this? So previously, people, when people talk about the stellar dynamics of star clusters, they mostly put them in isolation, or they put them in this, dark matter halos, and to talk about their kind of a gradual evolution. But because we have our cosmological simulations with the orbits of individual star clusters, we can actually trace the behaviors of the orbits of all these star clusters during the cosmic time. So, it is much more complicated than we thought, because, the massive star clusters, they are actually formed from the very dense and gaseous disk at high redshift. And then they constantly interact with the giant molecular cloud within this clumpy disk. And then there are some mergers, and these mergers will destroy some of the clusters, but it will also kind of release some of the clusters to higher orbits, so that making this orbit very radial. And then because of this radial orbit, it crossed the gas disk repeatedly, getting this very strong tidal disruption when it crossed the disk with the disk shock or bulge shock. So it is a very complicated dynamical process. And really, this is not I would say, this is definitely not an ideal place to study stellar dynamics as we thought before. I would say this is a nightmare for people to study the dynamics, because there's so many complicated processes. It was until very late that these globular clusters are thrown out to the halo, so that these things becomes more clear. So to study the tidal evolution, we kind of use a tracer of kind of the tidal, this second derivative of the potential as the tidal tensor, and use the eigenvalue of the tidal tensor to study the kind of history of the tides. And you can see these are extremely complicated in the last, during the first 7 or 8 gigayears of their simulations. And then we, based on this dynamical tidal history, we calculate the dynamical evolution based on the n-body calibration. And we find that the initial power law slope of these clusters, cluster mass functions, becomes much more shallower, and at the end of the simulation, at the high redshift 0, the mass function is kind of similar to the one that we observed at the current at present at high mass end. But in the low mass end, we are still overestimating the mass function, so we are still investigating this. And also, so this is the mass, this is the distribution of these clusters in the age and the metallicity plan. And you can see the formation of this globular cluster, they're not always formed at very high redshift. So there are some globular clusters that are formed at redshift 10, but there's a large range of their formation epoch, all the way down to redshift 1. So the age metallicity distribution has this kind of shape. So this is something that we predict repeatedly for different sets of simulations. And you can also check our newest version of this simulations with this archive that we put out last week. So another topic is that, do we really need a special conditions for globular clusters to form in the simulation? So one thing that we noticed is that the majority of these surviving clusters are formed with this at this peak epoch. And these epochs actually represent the major merger epochs of this set of cosmological simulations. We find that 70% of the most massive clusters are formed during these 4 major merger events in the set of simulations. But as I said, these are still the low resolution simulation that we cannot resolve the individual star clusters. So we want to test whether our results of this merger-driven scenario make sense. So that's the reason, Federico and I have been running a set of galaxy merger simulations with very high resolution, so that the massive star clusters can be resolved individually up to down to 10⁴ solar masses. And we use the SMUGGLE framework in the repo that have been developed by Federico to study how the galaxy mergers affects the dynamical evolution or the formation efficiency of the star clusters in the idealized system. So what we find, so this is the kind of the density snapshot of these galaxies, galaxy merger pairs. And any questions? No, I'll go ahead. Okay.
I don't think so.
Okay. So one thing that we notice is that both the mass function of the giant molecular cloud and young massive clusters can be described by a power law shape, and with a power law slope between -1.5 to -2.5. And one thing that is very interesting is that the slope of this power law becomes much more shallower during the 2 merger events, and the high mass cutoff of the stellar mass, the mass function of the young massive clusters can extend to higher masses during the merger as well. So these 2 effects actually is the reason why the more massive clusters can be formed during the merger events. And also we calculate the same thing is the time evolution of the cluster formation efficiency. You can see that there are some distinct peaks of this cluster formation efficiency during this idealized simulation. And these peaks actually corresponding to the first passage of this merger, and then the second passage and the final coalescence. And this efficiency is not only depends on the star formation rate surface density of the gas, but also is a strong function of the gas pressure that of the galaxy patches. So we actually argue that it is the very strong, because of the merger, it triggers a compression of the gas, and then it leads to an extremely high pressure of the gas in the tidal dominated region. And it is this high pressure that leads to this very high cluster formation efficiency. And here, I think we demonstrate that the effectiveness of galaxy mergers on reproducing the massive star clusters. And so this essentially means that, probably the globular cluster population that we see can be used to trace the merger history of the different types of galaxies. So this actually brings out a new channel of tracing the assembly history of the galaxies by using their globular cluster component. So I think I'll stop here. My time is up. So I'll leave the very lengthy summary without reading it. But I would like to answer any questions that you have.
Okay, thanks a lot, Hoy. Are there any questions for the speaker?
Hi, Federico. So can I go on?
Yeah, sure.
Hi, Huy. Thank you very much for your very nice talk. I have a question about the slide where you were showing the orbit of the clusters. If I understand it right, it looks like they are okay in the right panel here. It looks like they are becoming more eccentric with time. How do you interpret these or explain this? I mean, the apocenter is becoming larger, if I understand.
Yes, exactly. This is an excellent point. So if you notice that don't notice the orbits this plot, you can see there are some kind of jumps of their galactic radius here, here, and here, and here. So these are actually 4 major merger events of the galaxy. So it is actually these star clusters that are formed from the halos, from this the central halo. But then there are some major mergers that kind of brings up the energies of the orbits and then disturb the galactic potential. And this is disturbance that lead to some fractions of the star cluster that go to higher orbits, but not all of these. So this is a specific cluster that I pick that have these effects. That once there's a merger, and then this cluster will be ejected to higher orbits. But I totally agree with you. There are also many clusters that when these clusters are experience this merger, they change their orbit dramatically, and the dynamical friction will lead to a very huge trend of sinking into the center. So there are kind of different fates of the clusters. But for this one, it is the merger that really triggers this kind of liberation of this cluster to the halo. So because this is a kind of the surviving cluster at the redshift 0, so it seems that they have to have the experience this ejection so that they can be brought to the halo regions, and then at the halo region, the dynamical disruption becomes less and less so that they can survive.
Okay, thank you. Thank you very much.
Vincenzo, do you have a question?
Yes. So I'm not an expert, so forgive me if I say something naive, but I was wondering if it would be possible to extend or to apply your simulations to the Magellanic Clouds, for which we have a very well-known, we have star cluster systems well studied, and for which it would be very, very useful to have, for example, an estimate of we see, for example, peaks of star cluster formations, if they can be reproduced by simulations, and also to see if a cluster can be taken from one galaxy, and now we see them in the vicinity of the other one. So that's the question.
I think that the speaker
Sorry, I think
disappeared. Okay, no, you're there, right?
Sorry,
Yeah.
I dropped. So I think there's some internet issue in the hotel. So sorry about that. Questions. I don't know whether you saw. Okay, can you still see my slides or not?
No, at least I
Okay.
can't.
No, we don't.
Sorry about that. It's just poor internet. Okay, questions?
Oh, yes. Yeah. Vincenzo, probably you have to repeat the question because Hoi was offline while you were asking.
Ah, okay. So
Really sorry.
the question was about Magellanic Clouds. If you could simulate galaxies like Magellanic Clouds, for which we have we studied the star cluster systems, and for which we imagine that we have that the interaction between the galaxies probably had an impact on the star cluster systems. Yes, basically that was the question.
Yeah, this is an excellent point. So this framework can actually be applicable to different galaxy systems. So actually, in our new series of paper from Braun, this is the PhD student of Oleg. So we extend our model so that we can run it into the local group environment. So we have this controlled initial conditions and twist the initial phase of the cosmological simulation conditions so that we find a local group environment. So that at the end of the simulation, we have a Milky Way and M31, and also some dwarf galaxies. But for this simulation, unfortunately, we don't have the very similar setup compared to the large and small magellanic cloud. But we are definitely interested in the subhalos and their globular cluster populations. We are still processing the data, and hopefully we can get some new results. And I agree, this is a very interesting direction, because recently, people find that globular cluster population is extremely abundant for dwarf galaxies. And I don't think people know exactly what is going on, but yeah, this is something that should be paid special attention to.
Okay, are there any more questions? Francesca?
Hi. Can you make prediction for correlation of number of globular cluster versus the dark matter of the galaxy, since this is typically used to, is an estimate to, yeah, okay.
Yeah, this one is so for this suite of models, so we have to focus on individual galaxy, one galaxy. For example, here's the Milky Way, because it's extremely computation expensive. It has a 3 parsec simulation resolution over a 10 megaparsec box. But it is quite promising that in our series of other projects, so this is me and Oleg in 2014, and we have some updated models with Choxy, the student, and we basically designed a suite of semi-analytical model that tend the globular clusters onto the dark matter halos in the galaxy cosmological simulations, with the assumption that major mergers, gas-rich major mergers, contribute a significant amount of star clusters. Based on these criterion, and we find that these linear relations are naturally arise. And so we are very excited about this. And both the normalization and this linear relation are reproduced. And we also reproduce a overabundant of dwarf galaxy, overabundant of globular cluster in dwarf systems. So so there are, that will be a whole talk for another topic. But I encourage you to check Lee and Gennady in 2014 and the Choxy.
Okay, thank you.
Thanks.
Any other questions?
Federico, I do have a question, but I don't find the raise hand button. So can I?
Okay, go ahead, sure.
Hi, this is Mario. I have a question about the different modes of star formation during merging. It has always been said that most of star formation occurs in clusters, but there are several theoretical works that during the past years slightly changed this view, saying that there is a significant fraction of star formation in galaxies, in our galaxy, that occurs in the diffuse medium rather than in very dense clusters. So I was wondering, during the merging between galaxies, does this ratio between the star formation occurring in clusters and star formation occurring in a not dense environment actually change?
So here is exactly the plot that try to answer your question. So this is the time evolution of this so-called cluster formation efficiency. And you can see that this merger has three sequences: a first passage, and then there's second passage, and then final coalescence. And actually, it corresponds to these 3 peaks of this cluster formation efficiency. And it is during the mergers, it really triggers a huge jump of cluster formation efficiency. And I totally agree with you that this merger really affects this modes of cluster formation. But in terms of the argument that was the whether the star formation is mostly happened in star cluster or not, this will go back to the definition of star clusters, right? So do you view open clusters as star clusters? For example, a couple of dozens of stars formed in the molecular cloud. Do you view these as star clusters? So I think it's always a mass-dependent definition. So that's the reason why we have this different cuts of definition of the star clusters in order to calculate the efficiency. You know, the higher the mass cut is, the lower this cluster formation efficiencies are. But we do find that the trends of this merger triggered boost of cluster formation efficiency is robust to this choice.
Okay, thank you.
Any more questions? Okay, if not, let's thank again Hoi for the very nice talk, and I guess we meet again next week.